All right, last time we started section 6.1, talking about rational numbers, talking about how, yes, they're fractions, but they're a very specific type of fraction. We looked at some examples and we talked about some historical relevance of fractions and where they've come from throughout the history. And today we're going to take a look at three different types of models. We saw these models last time. I just didn't identify them specifically for you. The first one is called an area model, and it's usually it uses a rectangle. It could use a circle or something like that too, but we're going to do an example so that you can see an example of an area model. So we're going to use the example on all of these as the example 3/4. And I'm going to show you what it looks like as an area model, a number line model, and a set model. So for 3/4, you need to divide this into four pieces. If you want, you can divide it in half, and then in halves again like this, or in half again like this. It doesn't make any difference. And 3/4 would mean shading in 3 of the 4 pieces. Okay, so that's an area model. We saw a few of those last time. We saw 2 of them on part A and part B on example 1. Part C is also an area model. It just uses a circle. A number line model is another way to talk about or to draw an image sort of the number 3/4. So we would start in this case at 0 and ending at 1, and then we would subdivide it in half and then in halves again, so they're each 1/4. So this would be 1/4, 2/4, also known as 1/2, and then 3/4. So the number 3/4 would be this spot right here on a number line. And the third one is a a set model, which uses chips. And again, we'll use the numbers 3/4. And we saw this again on example 1, where there were, whoops, I need that to be thinner. There were chips, and there were 4 of them. Tell you what, sometimes copy paste, I just do better to just draw them. All right, so there's 4 chips, way too close to the 3/4, and then we would shade in 3 of them for 3/4. So here's 1, 2, and 3. So 3 of the 4 chips are shaded in. These are all distinctly different models. They all represent 3/4. The first one is more of a part of a whole kind of picture. There's a whole object and it's somehow subdivided. The second one kind of is a part of the whole as well, but you have this sort of number line perspective. And then the third one is more like they're independent objects and you have a certain portion of them that apply with this description, a certain portion that don't. So the fundamental law of fractions is one that you have used a lot. And it talks about the fact that if you have a rational number or a fraction a over b, and if you multiply by the top and the bottom by the same value, it doesn't change the value of the fraction. You've been using that since late elementary school when you first started working with fractions, 4th, maybe 5th grade, somewhere in there is where it's introduced with this idea. And typically it's thought of in the other way, though. It's thought of the idea of reducing. Like a moment ago when I said that 2/4 is otherwise known as 1/2, right? I was using the idea, instead of multiplying by 2 on the top and the bottom, I was either dividing by 2 on the top and bottom or multiplying by 1/2. So you can do this with other values besides integers. But that is the fundamental law of fractions, is that the values in the top and the bottom multiplied don't change the value of the fraction. The simplest form as a result of that would be a rational number a over b, where the denominator is positive. Okay, so simplest form includes positives in the denominator. It could have a negative in the numerator, okay? And that the greatest common divisor of the numerator and denominator is 1. All that means is that a and b have no values that they can both be simplified or divided by. Okay, so that would be a simplest form fraction. So why is 2 over 4 not simplified? Well, because the top and the bottom can both be divided by 2. Why is 3 over 7 simplified? Because 3 and 7 don't have any values that divide both of them. Okay. All right, so place we're going to start here is to take this fraction, 7 over negative 14, and we're going to write 3 fractions equal to this. How many fractions are equal to this? It's sort of a trick question, but I think you all probably know the answer. Say it, Cameron. Infinitely many, right? There are infinitely many numbers, so there's infinitely many values that would be equal to this as well. So what I'd like for you to do is write down 3 fractions that are equivalent to 7 over negative 14. Okay? Write down 3 of them. Once you have 3 of them written down, turn to a neighbor and confirm that you and your partner, the person next to you, whatever, both have values that make sense, that you're not like, oh, no, I don't think so, that doesn't work. Okay? So check in with somebody nearby you. Has everybody had a chance to chat with somebody? If not, please do so. Check in with somebody nearby you real quick. Okay, somebody give me an example of one number that you have, one fraction that is equal to 7 over negative 14. Yes, ma'am. 1 over negative 2. Does that work? It does. Good job. What's another one you guys have?
14 over negative 28.
14 over negative 28. Fantastic. What else? I know that you have more because you had to write down 3 yourself, and that's only 2 of them.
4 over negative 8.
4 over negative 8. Okay. There's one more thing I want to mention just because nobody did mention it. Does the negative have to stay on bottom? It doesn't. So you actually could also write negative 7 over 14 even very simply as an equivalent fraction, simply changing where the negative is, right? That's equivalent to multiplying by negative 1 on top and bottom. So that would be another one. But yeah, like we talked about at the beginning, there are infinitely many things that you can create. They're all going to be equivalent to 7 over 14 or 1/2, right? With a negative either on the top or on the bottom. All right, take a look at this one. This says 42 squared over 35 squared. And the directions ask you to find the simplest form. Now let me give you one word of caution. When we talk about finding the simplest form, we're asking ourselves, what can I simplify the numerator and the denominator by with division or multiplication, right? So what you cannot do is you cannot do this. Why not? I mean, man, we're tempted to. They match, right? We like to cross out things that match. Why does it not make sense to cross those off even though they match? Yeah, you are taking the square root instead of dividing them out. That's true. And the equivalent phrase, or the equivalent expression here would actually say 42 times 42 on the top. And on the bottom, it would say 35 times 35, right? So if you were to try to take the square root or cancel out the squares, you'd be eliminating a 42 on top and a 35 on bottom. Yeah, that's not the same thing. So that's the problem with the square rooting the top and the bottom, is that you'd be eliminating different factors on the top and the bottom by doing so. However, if it's written like this, hopefully we can have some kind of idea of what we could simplify from each of these. So if we were looking for common factors here, what common factors do you see? 7. And not only do you see a 7 sort of like here, but you also see it here, right? So you can divide each of those by 7 and do it, I mean, not component-wise necessarily, but you can actually divide by 7 twice. That's what you're really doing when you're doing that. So we can divide by 7 twice. So if I divide by 7 once, I end up with 6 times 42 and 5 times 35. You don't have to do it in 2 steps. I just want you to recognize that you really are doing it twice. And then dividing by 7 again would divide by the second one. So you have 6 times 6 and 5 times 5. So how would the final answer actually look for this problem, whether you did it in 1 step or 2? What would you have? Yeah, 36 over 25. And I know that there are probably some of you who are just like cringing because the top is bigger than the bottom. I promise you it's okay. Okay, if there's questions that specifically tell you to change things so that that doesn't happen, that's great. But if it doesn't tell you, it's perfectly fine to leave it that way too. So this is a perfectly reasonable answer, right, like it is. There's another very interesting way to determine if 2 fractions are equal besides sort of simplifying one or multiplying the tops and bottoms of another one or so forth, is that you can, in essence, kind of look for if when you cross multiply you get the same value. In particular, if it's true that A over B is equal to C over D, then it has to be true that when you multiply across the diagonals, that AD is also going to equal BC. So these are equal, right? Only if they're both the same. Okay, so this is one of those like if and only if statements. If the bottom's true, then the top has to be true. If the top is true, then the bottom has to be true. All right? So if you take a look at the example we just did before where we had 7 over negative 14, and you tried to say that for sure that you knew that this was equal to negative 1/2, then it has to be true, again, that if you cross multiply, that you get the same value. And in fact, 7 times 2 is 14, and negative 14 times negative 1 is also 14, and so it works. And it doesn't just work, of course, for that one. It works for any equivalent fractions. So that's another way to determine if fractions are equivalent, is to cross multiply and see, do I get the same product in both directions? So the next question actually asks you to determine if 2 fractions are equal, 3 over negative 12 and negative 36 over 144. There are at least 4 ways to do this problem, and I'd like to show you all 4 of them for several reasons. Number one, because you may not like one of the ways I show you, and if I am like, man, you really have to do it this way, you're going to be like, well, why should I do it that way? I know a way I like better, all right? But more importantly, what I want to do is I want to be able to show it to you so that when you have students in your classroom and you show them something and they're like, that doesn't make any sense to me, and they say, Miss Mathis, I don't get it. Why in the world is that going to work? You can say, okay, well, if you don't like that way, how about take a look at it this way? And so you give them another option as well. Okay? So one of the ways is obviously the one I just showed you. Agreed? So let's take a look at that one first. So we'll call it number 1 as though it's our number 1 way. And it's the theorem that we just encountered, Theorem 6.2, which talks about this sort of cross-multiplying idea. So you have negative 3 over 12. In fact, are you guys okay with me ignoring the negatives? Are we all clear on the idea that they're both negative, so that's good? Okay. So we have 3 over 12, and we have, what was our other one? 36 over 144. And we don't actually know that they're equal. This is like us testing it, right? So this is sort of like a question mark for us. Are they equal? I don't know. I'm going to cross multiply and I'm going to find out, okay? So we're going to cross multiply. I don't necessarily think this is the best way to do this problem because the numbers are quite large. I don't expect that you're going to be multiplying 3 times 144 in your head. You might, but I wouldn't. I'd grab a calculator, and if I didn't have a calculator, I'd do it longhand because I don't do multiplication with that large numbers in my head. If you have a calculator, go ahead and grab it out. If you don't, please don't grab your phone. Just leave it put away, and we'll let somebody else who has calculators with them today do that. Somebody tell me, after you've grabbed your calculator, what is 3 times 144? What is it? 432. Okay? And then we're going to try the opposite diagonal. 12 times 36. What is 12 times 36? 432. Are they equal? Yes. So since they're equal, when I cross multiply them, they were equal to begin with. So, I mean, if you have a calculator, great. This method works really nicely and it's simple enough. All right? If you had to do it by hand, I don't think you'd probably choose to do it that way. So let's look at another option of how you might check to see if the values are equal. So this method I'm going to just find a common denominator, CD for common denominator, and we're going to do find a least common denominator in a minute. But honestly, you don't always need a least common denominator. A common denominator would work just fine. So let's take a look at this one. We have, again, I'm ignoring my fraction or the negatives for the moment. We have 3 over 12 on one side, and we have 432. No, I'm sorry. What was it? Start from the beginning. 36 over 144 on this side. That is a terrible 36. Wow. Let's try that again. Better. So hopefully when you look at those denominators, you kind of recognize that they have something that's kind of in common already. What do you recognize when you look at those denominators? What was it? They're divisible by 12, right? They're both divisible by 12. What else might you recognize? Huh? The second one is, the first one's not. Okay, we'll come back to my question here in a minute then. Take a look at this one then. What you might notice when you do this is that, like you said, they both have 12s in common, right? But they're not the same. Agreed? So when you have fractions that are not the same and you're not sure what to do with them, what you could do is just multiply them by each other. So that you multiply the 12 by 144. Of course, if you do it on the bottom, you have to do it on top, right? And you multiply, I don't have space there, and you multiply the 36 over 144 by 12 on the top and bottom. Okay, that will give us the same denominator, agreed? Yeah, it will. That will give us the same denominator. So when you look at 12 times 144, we know our denominators are going to match. Our question is going to be, what happens to the numerators? Will they match as well? So what is 12 times 144? Yes. And of course, the second one is also the same. So let's look at the top. 3 times 144. We already did that earlier, so we know it's 432. What about 36 times 12? 432. We happened to do that one earlier as well. Of course, if we were using this method, we would have been doing it right now. But they match, right? So this is a common denominator. It is not the least common denominator. So let me talk about the least common denominator next, which is where I was inadvertently going just a moment ago. A lot of times, in fact, I don't know why 12 is so important, but these days when kids learn their multiplication facts, they learn them up to the 12s tables. Okay, I don't know if you did or not. I didn't when I was in school. We only did up to 10s, but up to 12s. So most children would know that 12 times 12 is 144 if they've memorized those multiplication tables like they hopefully should have. And the reason that matters on this particular problem is because if I multiply the first fraction by 12 over 12, I get the 144 denominator immediately. Do you see that? So it's very friendly on this one to only manipulate the first fraction because I can get a common denominator, in fact the least common denominator, very, very quickly if I recognize that fact. And then of course 3 times 12 is in fact 36, right? So I find out that the fractions as well are equal. The fourth way to do this, which also works very well for this one, and again, some of these methods work really well in some fractions and some don't, but it works really nicely on this one, is instead of trying to find common denominators like that, what we actually try to do is to simplify and compare. I hope when you looked at the 3 over 12 initially, you thought they have something in common. And even if you didn't on the 36 and the 144, I hope as you're looking at them now, you recognize at least they're both even. So both of these fractions have the ability to be reduced, right? Numerator and denominator will in fact divide by the same value. On the first one, they'll both divide very nicely by 3. So 3 divided by 3 would be 1, and 12 divided by 3 would be 4. So you can get the 1/4 probably from the 3/12s pretty directly. I would be very impressed if you automatically knew that 36 over 144 is 1/4, because I wouldn't. Those aren't numbers I work with very frequently. But I might very quickly recognize they're both even. So I'm going to do this sort of in a lowest observable pattern kind of way, because I think we could all look at that and say, yeah, they're all divisible by 2, right? So if I were to take 36 and I divide it by 2, what do I get? 18, yep. And how about 144 divided by 2? 72. At the point when we get 18 and 72, you could go ahead and go again, oh, look, they're even, divide by 2, and maybe that's what you think and you see that and that's great, go with it. But you might also at that point recognize, oh, look, those are the multiples of 6, and you might recognize they divide by 6. Or, oh, look, those are both multiples of 3. So you might see a different factor. So I happen to see the 6s, probably because my daughter and I are still working on her multiplication tables, and we did 6s the other day. That's probably why. Man, she's still struggling. 18 divided by 6. 3, right? And 72 divided by 6 is 12. You see that 3 12s? That's what the other one started at. And we know from there that we need to divide by 3. So 3 divided by 3 is 1. And then 12 divided by 3 is 4. So we end up with the 1/4 on both of them, so they're equal. It's worth noting that if I got to this point right here, you could stop, right? I mean, because you already know it's equal to where you began over here. So that would also be a legit place to end your problem and to make a claim about it being equal. All right, so if a question asks you to determine if they're equal, do I expect you to do all 4 methods? Definitely no. Please don't. Pick which one you like and go with it. If it asks you to do it in a certain way, obviously you're going to want to do that. But unless it asks you to do it in more than one way or something like that, I'm not expecting that from you, okay? All right, not only can you determine if fractions are equal, you can actually determine which fraction's larger by taking a look at the cross multiplication factors. So if in fact that A over B is larger than C over D, and again you cross multiply, what will happen is that AD that I just circled will be larger than the BC of the other diagonal. So here, it does matter that you go in the right order, right? Top left-hand corners where we start, just like we would be doing if we were reading. But the direction will matter here. It doesn't matter when there's equality, but it matters when there's inequality symbols. All right, we're going to take a look at one where we have to put them in ascending order. So ascending means what? Going up. Yeah, Kurt says it's going up. So you're going to start with the smallest one, and then you're going to end with the largest one. There's lots of ways to do that. On this one, taking a look at the particular denominators that we're dealing with, 10, 20, and 5, hopefully you're thinking, boy, I could make them all 20 pretty easily. So the idea of trying to get them to all be the same is a really good one, and on this one it's not too hard to do that because they all have something in common to start with. So I'm not going to have to do anything to my 13 over 20. He's good to go. My 3 over 5, however, would need to be multiplied by what? 4, right? So what's 3 times 4? 12, so we have 12 over 20. And then I've got 7 over 10, so what would I have to multiply the 7 over 10 by? 2 on top, 2 on bottom, which would give me 14 over 20. All right, so comparing all of those when they're written over 20, it's a lot easier to decide which one's the smallest and which one's the largest. So which of those three in the boxes, thinking of the boxes themselves, is the smallest? 12 over 20, right? So this one is going to be like my number one value, but I'm going to write it the way it was given to me. So 3 over 5 is the smallest. What is the next largest? 13 over 20, and that's exactly how it was given to me, 13 over 20. And then the largest value is 14 over 20, which is 7/10, right? So that would be writing it in ascending order. All right, on number 6, it asks you to choose which symbol would go in between these two fractions, greater than, equal to, or less than. And again, I'm going to show you multiple ways to think about the problem. Obviously, according to the theorem we just looked at it a moment ago, one way to do it is to cross multiply. And some of us just get really excited about cross multiplying all the time, and that's okay. I contend that that's probably not the easiest way to do this problem because the numbers are kind of big. If you have a calculator, it's fine. I mean, sure. So we'll start with that way, but I want to show you a couple other ways to do it as well, just in case for some reason a child's like, okay, but that whole cross multiplying thing, it looks a little bit like you're waving a wand. Why is it true? Why does it work? And I think that that's a valid question to have too. So let's take a look at this one first from that perspective and show that we can in fact decide. So I have 51 over 215. And I'm kind of trying to decide what goes between here, so I'm just going to put a question mark. And we'll multiply this diagonal first. So what is 21 times 215? Please say somebody has a calculator because we're not doing that in our head, right? Emily does. Thank you, Alicia. 4515. How about the other diagonal? 51 times 430. Wow. No comparison at that point, right? It's the less than sign between, yes. The first one is smaller than the second one. So the correct symbol is going to be the less than symbol. But let me talk about some other options of how you might feel or think about this problem to determine what value should go between. On this particular one, you might consider maybe I would, try to get the same denominator because 430 and 215, do you see something in common? I mean, if I just double the 215 would be 430, right? So another option here, I'll actually title it, let me put it in here, would be to get a common denominator. Okay, is it always going to be the case that one of them's double the other one? Well, of course not. But when it is the case, man, it's really nice to compare. 21 over 430, and this one's going to be 430. And honestly, I don't care what the top is, but there's no way that 51 is going to be smaller than 21 when I'm doubling it, right? But it is 102, and it's very easy to see from there that the less than symbol is the correct one. The third way to do it, that we sometimes kind of dismiss when students say it or think about it, is something that I mentioned when I talk in number theory about checking your work when you're done, is to estimate it and see if something's reasonable. Right? Is that a reasonable answer? If you tell me that there's 213.72 babies born, we got something going on, right? Can't have 0.72 of a baby born. Like, it doesn't work like that. So looking at something and deciding, is it reasonable? And so one way to do this also is to estimate. Now, it doesn't work very well if the fractions are very close in size, but these fractions are nowhere close in size. They're significantly different. And if we take a look, so what were my fractions? 21 over 430. So if I take a look at 21 over 430, I mean, like, it's about 20 over 430, right? I mean, it's about the same thing. And that becomes really nice to just, cancel out the zeros. And then I've got 2 over 43. You could even say that that's approximately equal to 2 over 40 or 1/20th. Equal? No, but it's pretty close to 1 over 20, that fraction, by rounding things off. Again, if the fractions are close together, this is not especially helpful, but on this one, they aren't. So I have 51 over 430. So again, on this one, if I wanted to, I could say, well, that's approximately equal to 50 over 230. I can cancel out those zeros. They're kind of irrelevant. And I mean, I have 5 over 23, which isn't great, but I mean, it's pretty close to 5 over 20.
Wouldn't you do 51 over 215?
It should say 430, actually. That's what's wrong. I was just changing.
You were right on the second part, not the first part. Like
Oh, I wrote my denominator wrong. Thank you so much. Yes. Thank you so much. When I zoom in, I can't see all my screen. That's the only way I can write large enough, so that's what happens. 215. Thank you so much. So let's change that. You're right. I should erase all that, actually. Okay. Okay. So 51 over 215. So this is approximately equal to like 50 over 200. Wouldn't you agree? I mean, I rounded a bit more to do that, but it's not that far off. I can mark out a 0 if I'd like, and I'd have 5 over 20. But what is 5 over 20? Well, it's 1/4, right? So if you're comparing 1/20th to 1/4, those are significantly different. 1/20th is like a nickel, right? And 1/4 is a quarter in terms of money. 1/20th is way smaller than 1/4. And again, you can think of it as a less than value. Okay, just a third way of thinking about the same problem. Again, you get to pick when you're working on these problems. Any questions on those? Okay. Theorem 6.4 talks about the fact that between any two rational numbers, there's always another rational number. And that property is called denseness. So given any two numbers, you can always find a number between them. If you think about it from a graphical perspective, you guys have played with graphing calculators enough, or graphing on a computer enough, to know that you can zoom in and whatever you're looking at, it gets bigger, right? So what looked like there was no space or very little space between them, all of a sudden it looks like the space because you've zoomed in on the screen. And that's very much the idea of what's going on here. This idea that there's always space in between. One way to find something in between is to simply add the values together and divide by 2. It's an average, right? It's what you do when you try and figure out your grade, right? If you have 5 tests and you don't have any homework or anything added in, you add 5 tests together, you divide by 5. If you only had 2 tests, you'd add 2 tests together and divide by 2. It's the same thing that's happening with the denseness of the rational numbers. There's another way to do it, though, too. It doesn't find the number halfway in between, but it's a very nice way of doing it, especially when the fractions are ugly. Because I'm telling you what, I don't want to add 2 fractions together and divide by 2 if the fractions aren't already, like, having the same denominator or nice or something. So this one is actually a very friendly one. What you do is you add the 2 numerators together, you add the 2 denominators together, and you create a fraction with them. So instead of adding fractions together, you're just adding integers together, which is way easier than adding fractions together. So if you're taking a look at our example number 7, and you have 33 over 427 and 7 over 92, I'm telling you what, I don't want to add those fractions together. That looks terrible. I mean, we will add fractions together in 6.2, but really not that one. That's awful. So we can actually use what was just in the previous theorem, Theorem 6.5, and we can add the 2 numerators together, 33 plus 7. We can add the denominators together, 427 plus 92, and we can simplify. So the top is 40. What's the bottom? Somebody have it? 500 and what? 19. Yep, 519. 40 is going to be even, divisible by 5s and 2s, but 519 doesn't divide by 5s and 2s, so we're done. Nothing to simplify. so much better than adding fractions and dividing by 2. And then the question asked that follows it that says, why must there be a number between these fractions? And it is exactly what the theorem that was previously on my screen said. It's because of the denseness of rational numbers. So because rational numbers are dense, that is, you can always find a point I'm going to say halfway or partway, right? It doesn't have to be half, but partway is true as well, between two numbers. Now, before you dismiss that as like, well, duh, that's obvious, recognize that that's not true about whole numbers. There is no whole number between 2 and 3. There's a number, but it's not a whole number. So this fact is not trivial. It matters, right? It's something that's unique to the rational numbers that wasn't true before. All right. Consider this problem. A student simplified the fraction m plus n over p plus n to m over p. First question, what did the student do? Literally, what did they do? They crossed out the ends, which is something we sometimes do, but not like this, right? So what did they literally do? They canceled out. They probably would have even called it canceled. You guys didn't, but they canceled out the plus n. All right, that's what they did. And why might they believe that this is a valid thing to do?
Because it looks the same on top of the bottom.
Yeah. Yeah, and can you give me, it's Cassidy, right? Cassidy, can you give me a place where we can do that? Can you think of a case? Because it doesn't work here. Okay, somebody help Cassidy out. Can you think of a place where we can do that? If they're multiplied. Yeah, if it's multiplication instead of addition, this is totally a legit operation. Okay? So why might they believe that this is a valid operation? Well, honestly, because it works with multiplication. I did something on a previous screen when we had 40. I had 40 over, what was the number? 430? Is that my number? And I did this. Do you guys remember me doing that on the previous screen where I just marked out zeros? I actually had a student on a test do this, but not with zeros, and they had the number, I'm making these numbers up, I don't know what the numbers were. But they did it, and they did it with 9s. Okay, so they did the exact same, a college student in this class a number of years ago. And the issue is simply that sometimes when we're really being careless about what we're doing, students try to generalize things that are not generalizable. Right? Exactly like Cassidy said, well, they matched. Right? Well, they matched, so I just marked them out. It's exactly what this particular student was doing with this other very similar kind of example, probably because she saw me do it with zeros somewhere along the way. Okay, so this is not okay. Don't do this. This is, yeah, please don't do this. All right, but yeah, because they did it because it worked with multiplication, and probably because they felt like, well, it looks the same. It looks the same. So what might you do to help the student recognize that it doesn't work with addition? What might you actually do? An example is a fantastic idea, Emily. I have one written down, so we'll go with what I have. But let's say that we had 2 over, so we'll do 2 plus 3 over 5 plus 3. So if this worked according to the way they did it, we would be able to get this to say 2 over 5, right? Agreed? But if we actually added them together and considered it, I would have 5 over 7. How do I know? What's one way I would know that these are not equal? Right? Because if their way works, these should give me equal fractions. They're not equal, but how do I know that for a fact? There's lots of ways. Somebody give me one. Yeah. These numbers are really small, so cross multiplying is a fantastic way to look at this one. So if I cross multiply here, I have 14, and on the other diagonal, I have 25, right? So they're not equal. Yeah, they're not going to be equal. Another way to consider that is you could look at 2 over 5 and say, well, that's smaller than 1/2. It is, right? 2 is less than half of 5. And 5 over 7 is bigger than 1/2. Right? Intuitively, I could compare them that way as well as other options. All right, I want to show you one more example before we quit today. Example number 9. If we take a set of numbers equivalent to 1/3 and graph them as points on an xy axis so that the numerator becomes the x coordinate and the denominator becomes the y coordinate, what type of graph do we get? This is a very interesting problem, and it sounds way wordier than what they're having you do. So let me start with the 1/3 and ask you for an equivalent fraction to 1 over 3. What's another fraction that's equivalent to 1 over 3? 2 over 6. Wonderful. I need at least one more value. 3 over 9. Thank you so much. All right, we'll pause right there. The next thing it says to do is to take the 1 and make it the x coordinate and the 3 and make it the y coordinate. So this becomes 1, 3, 2, 6, and 3, 9. And just for good measure, because it'll help me to get the other half of the graph, can I write down -1 over -3? Are you guys good with that? Okay, so I'm going to use a -1 and a -3 as well. So I now have 4 points, and I'm going to graph them on a number on an xy coordinate plane, which I have over here. So here's my number line for my plane. And I need to do -1, -3, so that's right here. I need to do 1, 3, which is here. And then 2, 6 is here. And then 3, 9 would be here. What kind of graph am I creating? It's a line. This is the graph of a line. And it is. And every ordered pair along the line has that same ratio if I connected it well, which I didn't do a very good job, but just pretend for a minute. But there's one exception to what I just said. There is one point along this line that does not give me a ratio of 1 over 3. Any guess as to which one it is? 0, 0, right. 0, 0 happens to fall on this line, doesn't it? It does. It actually does. But it definitely, 0 over 0 does not equal 1 over 3. I'm sure somewhere along the way somebody told you can't divide by 0, dividing by 0 is undefined, things like that. But it does fall on this line. So over here when it asks you what type of graph do we get a line. It has a slope of 0. I'm sorry, slope of 0, slope of 3. But 0, 0 is not on this line. So if you were actually drawing this, what you would have to do is you'd have to draw the line like I did and then put a hole right there at the origin at 0, 0 to indicate that that's not an acceptable value. Okay?